Today's lab is about the common collector amplifier. So far, we've studied the common emitter and a couple different variations of the common emitter, and today we're going to look at the common collector amplifier. So a common collector amplifier would look something like this. The biasing circuit on the left here, R1 and R2, that can be many different things. Like that can be a regular base bias where you just have one RB resistor, or it can be like this where it's voltage divider. But what the key difference is that your input is still on the base terminal, which is the same as it is with a common emitter amplifier. But with a common collector amplifier, you're taking your output on the emitter instead of on the collector. So notice that I don't have a collector resistor. That's not a requirement of this configuration, but this particular variation of it doesn't have that. But the main way to tell that this is a common collector amplifier is that my output is being taken from the emitter as opposed to the collector. So to say that again, if I have a collector resistor and an emitter resistor, that doesn't necessarily mean it's common emitter or common collector. The key thing is where you take your output from. So if your output is from the collector, then it's a common emitter amplifier. If your output is from the emitter, then it's a common collector amplifier. And again, the word common in the naming there means that that point basically becomes a reference point. So this amplifier is called a common collector amplifier, and here's the collector, right? So what's common about this collector? Well, we know that when we're doing AC analysis of this circuit, this DC source looks like a short, right? Looks like a connection to ground. So in that way, it's almost like this collector is actually grounded from the AC circuit's perspective. So that's why it's called common collector. Like before I told you common meant the point that's like the reference point or the ground point. And it's not immediately obvious when you look at the circuit why the collector is deemed to be grounded, but it's only in the AC equivalent circuit that the collector seems to be grounded. So remember, when you do the AC analysis, you're going to replace VCC with a connection to ground. So it is like the collector itself is grounded. So again, like there's three different terminals of the transistor, right? Base, collector, emitter. You can apply an input on one terminal of the transistor and take an output on a different terminal. And then based on the two terminals used, that will determine the name, right? Common emitter means I apply my input on the base, take my output on the collector. Common collector is I put my input on the base and take my output on the emitter. And then there's one other configuration called the common base circuit where you actually apply your input on the emitter and take your output on the collector. All right, so this is the common collector configuration. It has voltage divider bias, like I said, but it doesn't necessarily have to. You could replace these two resistors with one resistor and just call it RB. That would work as well. That's not essential to the name common collector. All right, so we're going to go over this in lecture probably today, but the voltage gain for this amplifier is actually very, very close to 1. So the expression for the voltage gain comes out to be RE divided by RE plus little re. Okay, so notice that in most cases, this little re value is very, very small. Like we've seen a few calculations of little re before, the dynamic emitter resistance. That's often a few ohms to maybe like 50 ohms, probably maximum. So it's often a few ohms to maybe tens of ohms. So this value is pretty small. And RE, depending on the size of RE, most of the time this ratio here is going to be pretty darn close to 1. Right? So if you think about, even if I have like an RE of 1K, right, it would be 1K over 1K plus like 10 ohms. So this ratio is going to be like 99999. It's going to be very, very close to 1. And even if RE gets a bit smaller, even if RE is, a few hundred ohms or something, then this ratio is still going to be pretty close to 1. So again, I think I mentioned this before, you might ask, why would I ever want to build an amplifier that has a gain of 1? And the reason is that this amplifier has other advantages besides voltage gain. So the two main advantages of common collector are that it has a very high input impedance, because the input impedance is large because this emitter resistor here is not bypassed. So if we talked about it, I think in the previous lab, that if you attach a capacitor across RE to ground, that will actually improve your gain quite a bit, but it also lowers your input impedance quite a bit. So with the common emitter amplifier, we can put a bypass capacitor or not, and that will affect the gain or the input impedance. But this amplifier, because RE is not bypassed, that means the resistance seen looking into the base is going to be beta times little RE plus beta times big RE. So the input impedance of this amplifier is usually pretty large. And that's really good to help your signal couple to prevent that attenuation. Having a large input impedance is desirable because it helps minimize that attenuation that you get on that input voltage divider. Let me pull up some notes. Okay, so remember this from lecture, this discussion about the attenuation that we get on the base and attenuation on the input and attenuation on the output of the amplifier. So remember, we ideally want to make the input impedance as large as possible. If we were to do that, that would make this voltage divider, that would make the voltage divider close to 1 as we can make it. So the larger the input impedance, the larger ratio right here will be. The closer this ratio will be to 1. So that's desirable. And also for the output impedance, we haven't talked about that for this amplifier yet, but the common collector amplifier has very low output impedance. So we can actually make this ZO pretty small, like a few ohms or tens of ohms or something like that. So the common collector amplifier has a voltage gain of 1, but it has a very large input impedance and a very low output impedance. Both of those properties are very desirable for minimizing the loss that we get in the input and output side. So it's not good for voltage gain, but it's good for coupling the signal into an amplifier. So a common collector amplifier is often used as part of a multi-stage amplifier. All right, show you a picture of that actually. So it's actually pretty common to use a common collector as like an input buffer over here, and also to provide very low output impedance. So a typical arrangement you might see is we use this is a 3-stage amplifier basically. I could connect my load over here on the right, and then I could connect my input over here on the left, but it's just too much to show on the screen right now. So I'll just leave those separate for a moment. So this would be a 3-stage amplifier. So over here, we would have an input stage, and over here you have an output stage. And then in the middle, this would typically be your, where you typically want to get a lot of voltage gain in the middle. So anyway, the input stage would often be something like a common collector. The output stage would be a common collector. And then in the middle, you'd use a common emitter. So the common emitter would give you a large voltage gain. The common emitter would have a large voltage gain, but would have, kind of medium to maybe even poor Z in and medium Z out, which is not ideal for example, driving a very low output impedance. Right. So if you wanted, like I keep talking about the speaker as an example, if you wanted to attach like an 8 ohm speaker to a common emitter amplifier, if your output impedance is like, 1K or 2K, then, only like less than 1% of the signal is going to actually make it to that speaker. And that's just not acceptable. You're making a heater instead of an amplifier at that point. Your amplifier circuit is not delivering any of the voltage that it's getting to the actual load. Then why are you doing it, right? So you can just attach a common collector to the input side and a common collector to the output side and create this like multi-stage amplifier, and this will solve a lot of those problems. You can use the middle stage to get your voltage gain, and you can use the input stage just to make sure that you're getting as much of the signal into the amplifier as you can. So this would be like a high Z in and low Z out, and same thing for the last one, high Z in, low Z out. And also the voltage gain is about 1. And so this is a common thing to do. This is basically acting like what you would call a buffer. Like these amplifiers on the input and output are acting like buffers. So you may have heard that term even in, I think maybe I said it in the digital class. There's lots of different types of buffers. There's like a digital buffer, like the opposite of an inverter. There's buffers in programming, and there's buffers in circuits like this. So you may have also heard in like ETE 2101, any of those who have taken ETE 2101, you may have also heard of an op-amp circuit that has a gain of 1, right? So if you've taken 2101, you may have seen this circuit before. This is also called a buffer. So this buffer from 2101, this op-amp circuit, it's got the same idea. You might say, well, if this buffer has a gain of 1, just like the common collector amplifier that we're studying right now. And you might make the same argument. Why would you ever use a buffer? Why would you ever use a circuit with a gain of 1? Like, what does that actually do for you? Well, one thing it does for you is this is basically like if you remember the ideal op-amp rules, the ideal op-amp rules says that no current flows into any of the inputs, right? So the magic of this buffer amplifier with an op-amp is that it's able to basically copy whatever voltage is present on the input. It's able to copy that to the output without drawing any current, right? There's no current flowing in there. So think about the implication of that. You know, we always talk about the loaded voltage divider. We talked about this, I think, back when we were studying voltage divider bias, right? If you have a circuit like this and you wanted to make, you wanted to make a voltage that's exactly half. I think we used the example of 10. We said that let's suppose that we wanted to make a voltage of 5 volts. So we make these two resistors equal to each other. And then the problem is that when you try to connect things to the circuit, right, what will happen is this resistor RL will appear in parallel with R, and they'll combine in parallel, and that will drop the total resistance here, which will drop the voltage. So if you wanted it to be 5, after you connect that load, it won't be 5 anymore, right? So one thing you can do is, and let me say this also, the reason that it won't be 5 anymore, you could also say, is that RL is going to be pulling current, right? So if RL was not pulling any current at all, if the current flowing into RL was 0, then that would mean that RL looks like an open circuit. So RL wouldn't be affecting that voltage divider at all, right? But if a lot of current is going towards RL, then that means that it would affect the voltage. So what you can do is actually just attach a buffer amplifier there. So this is another basically application of a buffer amplifier. You can just attach this whole circuit right there like that, and then connect your load over here on the output. And then now it should be a little more clear why you'd ever want to have a circuit with a gain of 1, right? Because all this buffer does is provide a gain of 1, right? So whatever voltage it sees here, it essentially copies that voltage to the output. But the magic part is that it does it without pulling any current from whatever it is it's measuring. So if it was pulling current, then it would alter this voltage divider, okay? But if it's not pulling any current, then that means this voltage divider will remain the same as it was before I connected this op amp. But at the same time, I can connect something else to the output of the op amp. So you can see the name buffer, right? You know, like you think about like a buffer of like a country, for example, you know, a country, two countries separated by one country in the middle. That middle country acts like a buffer, right? It separates the two sides. So buffer in this context means kind of the same thing. Like it's separating this voltage divider from this load. So that's kind of what we're doing here with our common collector amplifier. We're using this as a buffer, and we're using this as a buffer. And again, the advantage here is that we have a high input impedance and low output impedance. So this will be really good at capturing as much of the signal it can, you know, depending on the value of RS, right, and ZS. If you can make the input impedance very large, then that means most of the signal is going to come in. Even if the gain is only 1, it's got a very high input impedance and very low output impedance. So that just makes it really good at capturing that signal. Then once the signal is already into this first stage, then when this first stage drives the input of the second stage, like in this part of the circuit here, yeah, the gain will only be 1, but this Z out will be very, very small, maybe like 10 or 20 ohms. And if it's the common emitter amplifier, Z in will probably be hundreds or kilo ohms, maybe a couple hundred ohms up to like kilo ohms. So the input impedance of a common emitter is not great. It's not terrible, but it's not great either. So it's good to put this common collector stage in front. That way it gives you all the benefits of having a large input impedance and a small output impedance. Then you use this middle stage here to actually provide your voltage gain. And this middle stage shouldn't really have any trouble matching up because the output impedance here will be very low. So if the output impedance here is low, that means that most of your signal is going to make it to the input of the next amplifier. And then the output impedance here is not great, right? It's medium. It can be 1K or 2K in some cases, but we can make the input impedance over here much larger. So that means that most of the signal will transfer between there and there. And then finally, if we wanted to drive a very small resistance load, we can do that with a common collector because the output impedance is so low. So this is, I mean, I would say that a common collector amplifier is not often used on its own, but it's often used as part of a multi-stage amplifier system. Okay, on its own, it's not great because the voltage gain is 1, but it has other desirable properties, just like this buffer amplifier does. Let's get back to the handout. So now we'll go over and lecture how to derive the expression for this, but for now you can just use this expression. The voltage gain is RE divided by RE plus little re, and this is the dynamic emitter resistance. That's the same as before. This is actually the same input impedance that we got with, this is the same input impedance you would get if you had a common emitter without the bypass capacitor, right? So remember, the bypass capacitor will short out RE. So if you shorted out RE, then it's going to reduce your overall input impedance. You want to make this part, it's basically this part of the equation over here. You want to make that as large as possible. And if you shorted out RE, if you made RE equal to 0, then that's obviously not going to be very large. Okay, this part of the text actually talks about how, you know how we're always saying that when we're looking from the perspective of the base towards the emitter, everything that we connect to the emitter appears to be multiplied by beta. This is telling you that it's actually the opposite when you're looking from the emitter towards the base, right? So instead of looking from base to emitter, you can also look from emitter to base. So imagine you're looking into the emitter terminal towards something connected on the base. In that case, instead of multiplying by beta, you're going to be dividing by beta. Or, I mean, you're basically not going to, I won't say dividing by beta. I'll say that you're basically not going to be dividing by beta. So when you're looking from the emitter side towards the base, you don't see this resistance in here as beta times RE. You see it as just RE, right? So there's different ways to think about that. You can think about it as, you can think about it as beta RE divided by beta. Like looking at this piece of the circuit, you can think about it as, oops, not VN, it's V out. But if you're looking in there to find the output impedance, you'll see that when you look this direction, you're looking from emitter to base. So instead of saying beta times RE, you're going to be dividing by beta. So anything I connect over here, I'm going to be dividing by beta. So that can be a little confusing because it's like whether or not you started with beta RE or whether you started with just little re. So that when you're looking from emitter to base, then you would see that as just little re. If you're looking from base to emitter, then you'd see, so you multiply by beta when you're looking from base to emitter. And when you're looking from emitter to base, you don't multiply by beta, okay? So what's going to happen is you're going to see little re when you look in this direction, and then you're going to see big re when you look down here. So remember, finding the output impedance or input impedance is simply finding the resistance seen looking between these 2 points, looking between your out terminal and ground. So imagine sending a current in and watching how, it splits and combines and all that. So you send a current in here, some of that current's going to go down and some of that current's going to go up, and then it's going to recombine back down on ground. So little re is going to appear in parallel with capital RE, depending on what you have connected over here. So you're going to end up getting an output impedance that's pretty much little re in parallel with capital RE. And we know that little re is a value much, much smaller than capital RE most of the time. Little re, like I said, is 5 ohms, 10 ohms, 20 ohms, something like that typically. So it's a pretty small value. And if you parallel that with hundreds of ohms or even kilo ohms, then obviously the output impedance is going to be dominated primarily by this little value, little re. Okay, so yeah, this is the main advantage of the common collector amplifier is that it has a very low output impedance. So you can see the output impedance is basically just little re, right? So it's actually little re parallel with capital RE. But since little re is so much smaller than capital RE, then this basically approximates down to just being little re. So that means we can get an output impedance of a few ohms or 10 ohms or something like that, which would be great if we're trying to drive a load that has a very low impedance. All right, so if you actually connected a load to it, then that load would be connected basically over here, right? The load would be connected to the output terminal to ground. So anything you connect there would basically appear in parallel with capital RE there. So our voltage gain would change a little bit. It would be the parallel combination of that instead of just RE by itself. It would be the parallel combination of RE and RL divided by the parallel combination again plus little re. So that won't change the overall gain too much, because what's going to happen is that little RE is still probably going to be quite a bit smaller than the parallel combination of those two. So it depends on what the value of RL is, of course, but in most cases, this is going to be pretty close to 1 still. Input impedance wouldn't change too much, but it would, instead of just RE, you'd have RE parallel RL, and output impedance the same. That's not going to really change much because little RE is going to dominate everything there. Okay, so this is the circuit to build. It's a voltage divider bias, and it's a 1K emitter resistor here. So notice we're applying a pretty large signal now. We can do that safely because our input, our amplifier gain is only a gain of about 1. So we don't have to worry about making the gain too large and, causing clipping to happen. So we don't have to have a very small input signal like we used, I think 20 millivolts in the lab the other day for that other amplifier. So for this one, we can apply a pretty large signal and it's fine. All right, so we're going to go through a similar motion as we did before. We're going to measure the input and output voltage, measure the input and output impedance, and then use all that to come up with the gain expression. We're going to verify the gain by measuring the output signal and the input signal and comparing their amplitudes. And then we're going to measure the input and output impedance like we did before by connecting a load and not connecting a load. So the same kind of, even though this is the common emitter circuit, I just didn't want to redo that picture. It's the same process for measuring input impedance. So there's a note here that this is not the circuit that you're actually measuring. This is just an example of how to measure the input impedance. All right, so I'll go ahead and just build this up real quick. 180K, 680K. All right, let me attach a source to it. Let's add 4 volts peak to peak, 4 volts peak to peak, 1 kilohertz. So 1 kilohertz is the default frequency, so I'll leave that. And I think it was 15 volt supply. Setting up the DC biasing point is a little different in this circuit because it's voltage divider, but there's no collector resist. There's not going to be any drop over here. So remember how we said that we often want to set up our DC biasing point so that DCE is roughly half of whatever the supply voltage is. So if you think about it, we basically want 7.5 volts to be across the transistor here if we have a 15 volt supply. So what that'll typically mean is that you want about 7.5 volts here, DC, and then up here you'd want to have about 0.7 higher. So you actually have to set a pretty high voltage divider. But this is going to be a little different because from the Thevenin perspective, this is not going to satisfy that beta RE greater than or equal to 10 R2 because of the values I've chosen here. All right, so I'm going to measure the output with an oscilloscope. I think these were 100 and the emitter is 1K. So sometimes these convergence errors are related to nodes that are kind of almost floating. So you can see, for example, this node over here on the other side of the capacitor. So it's it's almost like this node over here is floating because there's nowhere for current to go. Like if the simulator treats this oscilloscope as an ideal instrument, then that means the instrument doesn't draw any current, right? In real life, this oscilloscope would actually have a 1 mega ohm impedance. So the oscilloscope will draw a tiny amount of current, but that's usually negligible compared to every other current in the circuit. But in simulation, it's probably treating this oscilloscope as an ideal measurement instrument that doesn't draw any current at all. So it's almost like this wire right here is floating. It's not connected. There's no path for current to go, right? So there's nowhere for current to go into this node over here and then out. So you can either change your simulation settings or you can actually attach a very large resistance over here to ground. Let's try just changing that setting that was it this class, or I think maybe it was 2301, the other class. This shunt resistance from analog nodes to ground. Often when I change that to something smaller, like 1 mega ohm, then it tends to work better, I've noticed. Let's see if that fixes that simulation error. You generally don't want to do that convergence thing because, you can, but it takes a long time typically. That convergence error fixer thing, it takes quite a while to actually fix the problem, usually several minutes. Okay, so that seems to have fixed my issue. So again, you can either connect a very large resistance right here, or you can actually just go into the settings and change it. It could be a problem over here as well. Well, no, I guess this is a source, so that wouldn't cause the problem. So you wouldn't need to do it over here. But whenever you see that simulation error pop up, look around in your circuit and see if there's anything that might be construed as an open circuit. Oh, still happening. Just takes longer for some reason. It seems to work for a while at least. And my output signal looks pretty good. Okay, let's try to measure input and output at the same time. I'll use channel A to measure the input, and then I'll use channel B to measure the output. Let's change the color of this. Let's do red and green, I guess. So red is my input and green is my output. I was going to say, I hope I'm on different scales. The two should look exactly the same in amplitude, so I was a little alarmed that they didn't. But it looks like I'm on different scales here, so yeah, that's better. Let's set them both to 1 volt per division, since we're looking at a 4 volt peak-to-peak signal, so we can easily fit that on the screen. Okay, so it looks good. You can hardly tell that red waveform is even there, right? So you have to like shift it off a little bit, use the Y position to even see the difference. So when I have the offset the same, like when both of these channels are set to 0 Y offset, then you can hardly tell that there's actually two different signals there. So I think that pretty much validates the fact that the voltage gain is 1. Okay, so that's a picture of the input and output. If you wanted to do that measurement for input and output impedance, I think in the lab we typically do it with a multimeter. So you do have a multimeter you could use in multisim. You could use to do that. Just make sure you set this to AC instead of a DC. So you could measure, like you can connect a test resistor here, measure the voltage with and without that test resistor, and then use that to determine the input impedance. Let's do that. If I put that 1K resistor in series, let's measure it. So I want to measure the voltage at that point with respect to ground. So I'm going to connect it like this. So I'm measuring the voltage on the other side, the left side of the capacitor with respect to ground. And I'm doing it with the multimeter on AC voltage mode. Okay, so I'm getting 1.392 with the test resistor. And then if I took that out, I get 1.414, 1.392. All right, so to remind you what this is doing, we don't know what Zn is, but we know what our test is. We're trying to basically experimentally measure what is Zn. So we have a known voltage source, and we have the voltage output of this voltage divider. So this value would be the 1.392. This would get smaller. This would be the 1.414 that we started with. Remember, the higher voltage comes when you measure without the test resistor. So if you measure this point without the test resistor, then you're going to get the larger number, right? When you insert the test resistor, you're going to get a little bit of drop across that resistor, and that's going to bring the voltage down. I shouldn't really call this V out because that can be ambiguous, because sometimes we're talking about input and sometimes we're talking about output. Let me just call that like Vx or something. Okay, so we're doing this, right? So you can just write a voltage divider expression, Vx equals Vs Zn over R test Zn, and solve that for Zn. So if you did that, you can do like Vx R test plus Zn, like cross multiply, equals Vs Zn. If I just multiply this denominator to the other side, and now I can get the terms separated. So I can write this as Vx R test plus Vx Zn. We'll just distribute that out. And then now you have this Zn term you can manipulate. So I want to move that to the other side. So I can move that to the other side and by subtracting from both sides. Then I'm going to factor it out. So if I factor it out, I'll just have Zn by itself over here. So I'll have Zn Vs minus Vx equals Vx R test. And then lastly, you can divide both sides by that Vs minus Vx, and you'll get Zn equals Vx R test over Vs minus Vx, right? And Vx is what we just measured, the 1.392. R test is the 1K. Vs is basically the source voltage before you connected the test, which was 1.414, and Vx is again 1.392. So that should be the input impedance there. And that's basically what we're doing. We're connecting this resistor and then not connecting it, and that's going to cause a drop or no drop here. And we're just measuring how much it drops and then using that to solve for the unknown Z in here. All right, so I don't have MATLAB open right now, but you can play with that. So that would be like a measured input impedance, and then you can compare that with theory. So this would be like this would be the measured Zn, and then you can compare that with the theory, right? The theoretical Zn. The theoretical Zn was R1 parallel R2 parallel with beta little re plus capital Re. All right, so you can easily compare these two values once you've done that. Once you've calculated it this way and measured it this way, you can compare those two values. And then for the output impedance, it's a similar process. You're connecting a load or not a load. So for ZO, it's your amplifier looks like this. So what we do in this case is we measure with and without. Right, so we can't take out ZO, right? That's internal inside the amplifier, inside our transistor, basically. And the only thing we can change is what the value of RL. So we can put different values of RL and see the change in voltage as we do that, and that should allow us to calculate it. But basically, when we measure there without RL, that's essentially the same thing as like RL equal infinity, right? That's like basically when RL is an open circuit. So when it's not even there, that's like this is looking like an open circuit. Then when you attach a known value there, then obviously it's not an open circuit anymore. So same kind of thing, you're going to get a voltage with and without RL. So let's check that. So let's do the same thing, but for the output side. The output should be on this other side of this capacitor. Yeah, I'm getting 1.405 without anything connected there. And then if I do connect a load there, let's see how it changes. So lab handout says to connect a 470 ohm there. I get 1.33. Okay, so think about what would happen if RL was equal to infinity, right? If RL was an open circuit here. So in this picture, if RL was an open circuit and you measured up here, there would be zero current, right? Think about this. If I replaced RL with an open, there would be zero current in the circuit, right? There would be nowhere for current to go. So whatever voltage I get on this source, it's not going to be able to provide any current anywhere. So that means there'd be no current through ZO there, and that means there'd be no voltage drop across it, right? So that means that whatever value this is, let's just call this, I don't want to call it AVVN because that's too long. I don't know, VY. Let's call this, or just call it VS, I guess. That's fine. So whatever value VS is, you're going to have that same value VS over here because there won't be any drop. Right? So that's how you can basically measure that. I mean, that's basically what that first measurement is without RL, is you're essentially measuring the source voltage directly. We'll put that back. Let's call this VX. So I'd have VX equals VS RL over ZO plus RL, just voltage divider. And I want to solve for ZO now. So go through the same steps. VX ZO plus RL equals VS RL. So I'm going to subtract this term VXRL to the other side and then solve for ZO. I can also factor out over here, right? I can do RL VS minus VX divided by VX. So that's how I can calculate that output impedance. And again, all those are known quantities. So RL would be the 470 that we attached. That's like our test resistor. VS would be the larger voltage, which was the 1.405. And VX would be the smaller voltage, so after it drops, which was the 1.333. So that should be my output impedance. Okay, so you can give that a try yourself to calculate the input and output impedance and measure it with and without the load to get the output impedance, and then with and without the test resistor to get the input impedance. And I think that's pretty much it. We've already verified the gain. Oops. It's going to be hard to show on multisim because the multisim equipment doesn't show the peak-to-peak. There's no peak-to-peak measurement on that oscilloscope. There is other oscilloscopes that probably have it, like maybe I think the Tektronix might. The Tektronix is okay. It's pretty good. I just don't like that it doesn't resize. Like the one thing I really like about this scope here is that if I wanted to, I could make it as big as I need. That's what I really like about the 4-channel oscilloscope there. But this Tektronix one is really old looking, but it does have measurements, I believe. Let's try to do that. So if you want to use this scope, it more resembles what you actually have in the lab. It looks like we're getting a little clipping actually. Anyway, we can measure, you can, on this scope, there's a measurement button up here, and then you can turn on some measurements so you can do peak to peak. That might be useful in some cases to actually have that measurement. I'll double check that value. Maybe I need to change a value here. I didn't notice it was clipping a tiny bit on the bottom there. Only when the load is connected though. I'm sure if we took that load away, that it would no longer be clipping. Looks good there. Okay. Yeah, I think that's all. There's some questions here for the analysis part. But yeah, basically we're going to combine all of those labs together. So we did 3 weeks of BJT amplifier labs so far. We did the common emitter. Then the second week we did common emitter with the emitter bypassed. And then today we're doing the common collector amplifier. So we can just combine all 3 of those into one report and make it a formal report. So I'll set the due date probably like finals week, at the end of finals week, I'm thinking. All right, so let's call it a day here. I will see you guys in lecture later today.
See you later, Professor.
Thanks. See you later.